Okay, so let's start with our first protocol, which is ICMP. So suppose that you are sending some data, right? Again, let me just tell you that what we are going to study today. So I will try to complete ICMP. Okay, so today we are going to see ICMP, network address translation, and then there is one thing, like since you know like almost all the layers, I mean, yeah, transport layer and application layer are not covered, and then but we will see that how all the layers are working together. Okay, so how all the layers work in unison. So that's what we are going to see together today. So let's just start with our first topic, which is ICMP. So what is an ICMP? It is basically one protocol which help us to make IP protocol reliable. So this is a protocol at network layer which help us which means in IP we do not have at the network layer, we do not have error control, flow control, these kind of things, right? So this protocol just help us to little bit make it more reliable, which means like it just help us to make error control, flow control, these kind of things. I mean, it just help us to provide the error control, flow control, these kind of things. Okay, so how it is helping, let's just see. So see here, IPv4 has no error reporting or error correcting mechanism, right? What happens if something goes wrong? Which means, for example, what happens if a router must discard a datagram because it cannot find a route to the final destination? Which means, let's suppose that you are sending some packet, and then this packet has been reached to this router. Some packet has come to this router, and then this router cannot forward that to anywhere because the destination is unreachable. Maybe let's suppose that that this router is connected to one network. Okay, so this is just one of the example. There will be many example for where we are going to use this ICMP. So I'm just going to take one of the example. So let's take one of the example where your router is connected to some network. In this network you have some host B. Okay, and then let's suppose like I mean the host was connected to some internet, some network here, and then this A has sent some packet to B. But by the time that A is sending some packet to B, at that time, let's suppose that this B got down and this B is not powered up. Suppose, okay. Then at that time, when this packet reaches to this router, let's suppose R, then what this router will do? First, it will check like where to forward this packet, right? Using its routing table. Yes. So first it will check where to forward. Then it will get to know, okay, you have to forward this packet inside its own network, right? If it has to provide this packet inside its own network, can anyone tell me what is the first step this router will do? It has to find the MAC address of this B, right? Using the ARP. Using ARP, R has to find MAC address of B, isn't it? So R will send a broadcast message which will say that, see, I know the IP address of some host. Can you tell me the MAC address? That's what R will say. Because if that's in the same network, then it will find the MAC address of B. If let's suppose that's not in the same network, let's suppose this is some other router R2, then it will find the MAC address of this R, right? It will find the MAC address of this R. But now this will find the MAC address of this B. But since B is down, so B will not even reply. So at that time, router will say that since I am not getting any reply, maybe this destination is unreachable, right? So the router must discard this packet, must discard the packet, saying that destination is unreachable, right? Is this clear to everyone? This is just one of the scenario where the router is discarding the packet. Obviously, there are many scenarios where the router may discard the packet, right? There are many scenarios. So this is just one of them. So that's what they are saying, that what happens if a router must discard a datagram because it cannot find a route to a final destination, or because the time to live has expired. So this is another scenario where the TTL has been expired, okay, and has a zero value. What happens if the final destination host must discard? So like, I mean, these are just examples. So these are the different examples. Let me just tell you the examples number wise. So see here, this was just one example. Now, if you talk about the examples, then these are the different examples. See, they are saying that first example is that what happens, the router must discard the datagram because it cannot find the route to the final destination, right? This is one of the example. So let me write number one. This is one example where the router must discard, or because the time to leave TTL field has been set to 0, right? This is another example. So these are the, let's suppose, two examples. Now this is another example. Let's suppose this is one and two examples. This is the third example. What happens if the final destination host must discard the receiving fragment of a datagram because it has not received all the fragments, right, within the predetermined time limit? So this may also happen that that router is waiting. Do you remember? I mean, sorry, final destination is waiting for the all the fragments to come. Do you remember the reassembly algorithm? What was the reassembly algorithm? It keeps on waiting for the, it keeps on checking for the offset. Yes. And the moment it finds that, okay, MF is 1, which means there are no, MF is 0, which means there are no more fragment, then at that time it will stop. So basically it will keep on checking. But suppose that particular offset has not come within the predetermined time limit, then in this case it will discard. It will not wait for forever, right? Obviously. So that is also one case where the router, also the final destination has to discard the packet, has to discard all the fragments. So this is another case. So let's call this case number 3. So there are many cases. I mean, you can have 20-30 cases where the router or the final destination has to discard. Maybe the one of the fragment has been lost. Maybe TTL has been expired. Maybe the host is down. The final destination, it is not able to reach to the final destination. Maybe there are examples of situation where the error has occurred. Maybe there is some error and because of the checksum, right? So this is because of the checksum. Let's suppose because of the checksum field in that IP header, and that is not matching. Let's suppose in that case also it may has to discard, right? Because the error has been occurred and the IP protocol has no built-in mechanism to notify the original host. So anyway, like there are many situations where the router or the intermediate or the router or the final destination has to discard the packet. So what will happen if the router or the final destination is discarding the packet? So in this case, this router will discard the packet. Why? Because this router is not able to hear the ARP request from B. Now, will it discard directly or will it send some message to the source, which is A? So there is some message called ICMP message, right? Whenever we are discarding, then at that time we send some message called ICMP message. So this router will send some ICMP message to A saying that, see, I have discarded your packet, and there will be a type like why I have discarded the packet. So basically, like it will also tell why. Okay, why means that type of the packet. So basically, I will tell you in just a minute. But yeah, there is a field called type, and depending on the type, maybe when the type is having some number, maybe 3, 4, 5, 11, 12, something like this. If the type is 3, then it is more likely that destination is unreachable. The destination was down, like it has reached to the final point, but at that time the destination was down. Maybe because that it is discarding the packet, then it will just write 3. 3 means the destination was down at the end. If TTL got expired, then it will just write 11, right? It will just write 11 that TTL was expired. So type and code, okay, and this code combinedly just tell you the more detail that why you have discarded the packet. So basically, in summary, like currently, I have not told you the detail, but overall, the idea is that whenever we are discarding the packet, we will also tell you, I mean, this router or the final destination will also tell the host that why we have discarded the packet. Not only they will tell you, they will tell that, okay, I have discarded. The host should know that why you are discarding, right? So that's why, like, why is also clear in the packet. So whenever I'm sending the message, then there is a field called type that will tell you that why I have discarded the message. Can I also tell that who has discarded the message? Who has discarded? Which means that if this router, who has discarded? Yes, that will also be told, right? I mean, it is better if the let's suppose this host know that who has discarded the packet. How? Obviously, if it is yes, very good, using the IP address. Yes, obviously, if this router is sending some packet, then there will be a source IP address, right? for this ICMP packet, there will be source IP address which will tell that who has discarded the packet, why has discarded. So both will be clear, that who has discarded the packet and why have discarded the packet. Okay, so these both questions will be clear. Now I hope that is fine, that to all of you, that why we are using this ICMP packet, why we are using, because if there is some situation, in that situation, if router or the intermediate host has, so router or the final destination has to discard the packet, then I will tell you that okay, this is the reason I'm discarding the packet. So that's one of the case. Another case may be that this host wants to know something. Okay, that's called query message. So there are two type of ICMP messages. One is the error messages. Another one is called query messages. Error messages are something when you have to discard the packet, right? When we have to discard the packet, at that time we will send the error message. There is something called query message. In that case, you are not actually doing the real communication. I mean, you are not sending the data. You are just curious to know something. Maybe let's suppose that these are the routers like this. This is the host connected to this. Maybe it can send the query message to maybe this, and then just to ask that okay, are you alive? Just to check whether this router is up. Are you alive? Then this router will say yes, I am. Okay, this is the response. So it will say yes, I am, just to check whether this particular router is alive or not. So I will tell in the more detail, but yes, there are two type of messages. One is called error reporting, another one is called query message. Okay, in GATE there has been a question where they have actually distinguished between error reporting and query message, and that was very good question. I will solve that question. Okay, so that's very good question. I hope you understood that what do I mean by query and error reporting. So basically query is just used to check whether that person is alive or not. Okay, or maybe some other query that the host or the router is having. And then error reporting is something that will actually check that I mean that will tell that why I have discarded the packet. Whenever I have to discard, then I will tell why I have discarded the packet, and for that I will be generating the error reporting ICMP messages. Okay. So again, ICMP messages are of two types. One is error reporting, report the problem that router or the host means destination here may encounter when it processes a IP packet. And query message is something help a router or the network manager to get specific information from the router to or another host. So basically this is just for the usual conversation. Maybe some specific information I want to know. One of the information is that are you alive? This is one of the information. This is also information to check are you alive. Okay, yeah. So now let's just see which error reporting type could be of different type. Maybe the TTL got expired, maybe the destination was unreachable, or there could be some other type of problems also. So although those details are not much important, on if the idea is clear, but let's just see those in detail, like what are those type of error reporting messages we can have. Okay, so let's just see. So see here, there could be many type of error reporting messages. Similarly, there could be some type of the query messages. Now what type of that message is? It will be clear from type and code. So generally it is clear from the type. If type is 8, then maybe it is echo request and reply. So I will tell you about this query message little later. So let's just first go to this error reporting messages. Okay. So this error reporting could be of any type. I mean, maybe destination is unreachable, maybe TTL got expired, like that, right? So let's just go to the first error reporting message, which is destination unreachable. Suppose if destination is unreachable, then in this case, like what do I mean by that? First of all, by destination is unreachable. So it means the most, okay, let me just read this. I've taken these screenshots from Frozen. So let's just read this. The most widely used error message is the destination unreachable. So it is having certain type, which is type 3, but you do not need to remember obviously these types. Maybe type 3 is the destination unreachable type. Okay. This message uses a different code to define the error message and the reason why the datagram has not reached to the final destination. So just for example, so see what does this destination unreachable mean? For example, code 0 tells that source that the host is unreachable. Okay, so maybe you are forwarding some packet, and then one of the case could be the host is down, right? So let me write all the cases here. So let's suppose that here in this there is a host B. Okay, one of the case could be host is down. This is also called destination unreachable. Okay, another could be, as they are saying, this may happen, for example, when HTTP protocol to access the web page, but the server is down. So another could be host may be up, but the port, okay, port is not open. Okay, maybe the port is unreachable. Port is unreachable. Host is reachable, but the port is unreachable, which means whenever you are sending the data, it may send it can get sent to this B, but this B cannot deliver to the port because port at the B is not reachable. Okay, so in that case also you will be sending the destination unreachable message. Now tell me, in this port unreachable case, who will be sending the ICMP message? This router or this B? In case of port is unreachable, if host is unreachable, router will send, right? If port is unreachable, then B will send. So in this case, B will send. In this case, router will send. Now, can anyone tell me, if both are of the same type, which is destination unreachable, then how this host, which A, right, the original source, will get to know that, okay, this is of, which type? Maybe the host is down or the port is down? Using the, yes, using the code. Yes, very good. So using the code, you will get to know that which one is the case. So if there are multiple cases in this destination unreachable also, there are multiple cases, and using the code, you will get to know that which case it is, right? Okay. So for example, when the port is unreachable, the message destination host is not reachable is created and sent back to the source, right? So there could be two cases, and there could be third case also, where which is also very popular, where I say that I have to discard the package because of the lower MTU and DF is 1. Okay, do not fragment is 1. In that case also we send the destination unreachable type, right? So do not fragment should be 1, right? Or should be 0? I think it should be 1, most probably. So if DF is 1, then I will say, and there is a lower MTU. Let's suppose this is facing the lower MTU. Okay, this is a lower MTU, but you cannot fragment. Then it will say that I cannot reach to the destination. Destination is unreachable, and it will also tell some information that what is the MTU. Okay, why I have discarded and what is the MTU. Yes, you can use this to find out the bottleneck MTU, that what is the MTU which is creating the problem, right? So that source at its own end can do the fragmentation, and you can avoid the fragmentation at later point in time. Why we are avoiding the fragmentation at later point in time? Because if there are more fragments, if one of the packet is lost, then you have to send the whole packet and all, and like there is more overhead, obviously. There is more IP headers that you need to make with the more fragments and all. So there is if there are more fragments, then the management is little costly. So that is why maybe I just need to have one fragment, and that is why the source may itself want to do fragmentation, not the in between the routers. Okay. So this was just one of the case when destination is unreachable. This was just one of the case for the error reporting. So it could be of any time. Maybe the destination is unreachable. Maybe the source quench. What does the source quench mean? Let's just see. Okay. Another type of error reporting could be of source quench. So what does the source quench mean? It means that if there is too much of congestion, if the traffic is too much, and because of that the router has to discard. Let's suppose the router is getting some packet. Okay. Let's suppose it is getting some packet, and then there is just too much of traffic, and then in this router there is a queue also. Okay, but this queue is also full. Let's suppose this queue is also full. Then can this router store this packet and later forward? No, right? So that's why this router has to discard this immediately, because there is no space. And suppose the network is also too much congested and router cannot even send on this network. So what will happen? Router will discard this packet, right? Discard packet coming from, right? Why? Because there was too much of congestion. See here what they have written. Another error message is called source quench, which is having a certain type, which informs the sender that network has encountered the congestion and the datagram has been dropped. Okay, because of the congestion, you have to drop the datagram. The source needs to slow down the sending more datagrams. In other words, ICMP adds a kind of congestion control or the flow control to IP protocol by using this type of message, right? So basically, ICMP is just a little help Why it is just little help, why it is not complete help, I will tell you about it. Okay, so but for now you understand like this, that if there is some problem, then at that time whenever we are dropping some packet, at that time we are going to send ICMP packet. Here the ICMP packet will be of type source quench. It will say that, see, there is a congestion, please slow down, right? Okay, now as I said, like there could be many type of error reporting. Now one of them is redirection. Let's just see that what is this redirection type of error reporting is. So it is also easy. So in this case, what happens, let's suppose that this router maybe something like this. Okay, let's suppose that this router is connected to these two routers. Maybe this is R1, this is R2, this is R3, and some packet is coming to this R1, and by mistake it is sending to R3. Okay, by mistake, maybe there is some mistake in the routing table, and by mistake it is sending to the R3. It was designed for R2, but by mistake you are sending to R3, let's suppose. Okay, so R3 will say that, okay, R3 will send an ICMP message to R1 saying that by mistake you are forwarding to me, although currently I am forwarding to R2, ultimately it should go to R2, let's suppose, right? So R3 will say that, see, I have forwarded your packet to R2, but next time you do not forward to me, it is just unnecessary work you are loading to me, right? You can directly forward to R2. So that's what this R3 will say, that, see, it is little lesser in the cost if you directly forward to R2. Maybe there is some mistake in your routing table. Okay, so no, R3 will not discard this packet. That's important here. So R3 will not discard this packet. There is no packet discard here. It is just saying that, see, currently I am doing your job, but please send from the next time, please send to directly to R2 only. Okay, please do not send to me. That's what this R1 will say. Let's just see that what they have written. The redirection message is used when the source uses a wrong router to send out its message, right? So maybe it is using this wrong router. This is a wrong router, but still it is sending to it. So the router redirects the message to the appropriate router. This is the appropriate router. Router is redirecting this message to appropriate router. Still, it is just saying that, okay, in future, okay, you need to change your default router in future. In future, if you want to send, please send to this R2, not to me. The IP address of the default router is sent in the message, and it will also say that, okay, I'm also telling you this ICMP will contain the IP address of this R2. It will say that, see, I am also telling you that what is the IP address that you should be using to forward it. Okay, so similarly, like, I mean, this is almost same as the case here when you were telling the M2U also. So basically, you do not only tell that why you have discarded and who have discarded, these kind of information is okay, but you also tell some additional information, that what is MTU, maybe in this case, what is the IP address of R2, something like this. Maybe some additional information also you can pass. So we discussed the purpose of TTL. Okay, so let's just see that why they have written this TTL here. We discussed the purpose of TTL in the field of the IP datagram and explained that it prevents the datagram from being aimlessly circulated in the internet. When the TTL value becomes 0, the datagram is dropped by the visiting router and the time exceeded message with the code 0 is sent. Okay, so this is again redirection message. This is again another type of error reporting, which is the TTL or time limit exceed error reporting. Yes, time exceeded. So this is another type of error reporting. When TTL got 0, then this router will send time exceeded, like time exceeded. It will say that, see, the time has been exceeded. That's why I'm dropping out your packet. So this is time exceeded type. Okay. Yeah. And it is having some certain type, which is 11 or something, right? And a certain message, which is certain code, which is code 1 or something. But yeah, these types, I mean, you do not need to remember these type numbers. Okay, so let's see one of other kind of error reporting message, which is parameter problems. What does this parameter problem means? I think this is covered, this is covered, this is covered, this is covered. Let's just see now parameter problem. Parameter problem is just like that. If some field get corrupted, maybe the source IP or any field can get corrupted, because of that the checksum is not matching. So parameter problem can be sent then when either there is a problem in header of the datagram, or some options are missing or cannot be interpreted. So basically there is something that router thinks that there is something wrong in the parameter, right? something wrong in the parameter meters, and because of that checksum do not agree. Okay. So in that case, it will send a message which is a parameter problem message. I hope you understood. Now let's just see that how it is actually sending the packet. Okay. So see here that what we are going to do. See, this is your received IP received datagram that you are going to receive from at any source or at the final destination, right? This is the received datagram. Now what you will do, you need to drop this because of some reason. Maybe host is unreachable, maybe the port is unreachable, or maybe the parameter problem, maybe TTL got expired. You need to drop this, okay? Suppose we need to drop this. Suppose we need to drop it. Okay. Then how we are going to drop? Are we directly going to drop, or we are going to send some ICMP message? We are going to send some ICMP message, right? That is clear to everyone. Now, how does this ICMP message look like? Let's just see this. Okay. So what I'm going to do, I'm basically going to put this IC like some part of this packet in the ICMP header. So there will be a ICMP header. There will be ICMP header. And what I'm going to do, I'm going to put some part of this packet. Okay. They see this was the packet that I wanted to discard. Now what I will do, I will take the IP header, maybe some 8 bytes. So 8 bytes will be, I think this will be a TCP or UDP header. Okay. Header. So these 8 bytes, if you look at the TCP header, these 8 bytes will be of the source port number, source port, destination port, I think sequence number, something like this, right? Actually, it will be having the port number for sure, because this is a TCP or UDP header. UDP header itself is of 8 bytes. I mean, this complete header is 8 bytes. TCP header is a little longer, but initial 8 bytes will be containing source destination, source port, destination port, like this, right? So these 8 bytes will be having that much information. Okay. So what I will do, if I need to discard this packet, I will take the IP header. I will also take the initial 8 bytes. What does this initial 8 byte contain? Maybe the port numbers and all, right? Okay, that's fine. So I will take some part of it. I will put that into the ICMP packet. This is the ICMP header. And what is the data of this? This is the data of ICMP packet. Then, do you remember the ARP packet? ARP packets and DSCP and these all, right? So ARP, if you remember, then ARP used to get encapsulated in Ethernet, right? Okay. Do you remember the DSCP? It used to get encapsulated in anyone? Or maybe RARP? Sorry, RARP used to get encapsulated in Ethernet only. And what about DSCP or the bootp? These used to get encapsulated in TCP or UDP packet, right? TCP or UDP. Similarly, this ICMP packet, okay, this is the whole packet that we have made. This is ICMP header, but similarly, this is ARP header, this is DCP header, but this again is going to get encapsulated in IP packet only. Okay, this is here. This ICMP packet, this whole thing is including the ICMP header and ICMP data. This whole thing is ICMP packet. It again used to get encapsulated in IP header. Okay. Now this IP header will be having the source IP and destination IP of the router that is discarding it. So let me tell you how it is working. Suppose that you are sending some data, okay, from this host A to B. Okay, let's suppose this is B. Now, whenever you are sending some packet, let's suppose this has to discard. Okay, maybe this has to or this has to discard. Let's suppose this is R1, R2, and this is R3. Suppose R3 has to discard. Then whatever the packet you are getting in that packet, what is the source IP? Source IP will be IP of A. What is the destination IP? It will be IP of B, right? The packet that you just received. Is this okay to everyone? Now, what I will do, if I have to discard this packet, I will take this IP header, maybe along with some part of the TCP header. I will take this. I will put this, right. I will put this in the, see here, this is the IP header, and this is your some 8 bytes, and I will also append the ICMP header, which looks like this. See, this is how the ICMP header looks like. So I will also append the ICMP header, which is telling me that, okay, what are the type and what are the code and all. So I will do one thing. This is the ICMP header. Although you do not need to remember this header also, right? Don't remember this. Okay, what is the structure of this header? Don't remember this, but I'm just telling you that you will encapsulate all of this into the ICMP header. So now you are going to have the ICMP header. Now to send it, either you need TCP header, either you need the IP header or you need the Ethernet header. I mean, you need one of the protocol. So in which protocol you are going to send this packet? IP, okay? Which means now you are going to again have the IP header. In that, what is the source IP? Source IP is of IP of R3. What is the destination IP? It is IP of A. Okay, this is your IP header, in which you are going to send this packet back to this A, because you will say the source IP is R3 and the destination IP is IP of A. So see here, that's what it is happening, that I'm again going to send back that to the original host, which is A, but this get encapsulated in IP only. So basically the hierarchy looks like this. Okay, so there is a popular diagram which looks like this. This is IP, and there are protocols like ICMP. There is one more protocol which is IGMP, like this. This is actually not much useful for the gate purpose. I mean, this is just it will just take 10 minutes. If you want to read it, you can read it from Fusion. 5 or 10 minutes it will take. It is for the multicasting purpose. Okay, so this is for the multicasting purpose, but yeah, anyway, like we are going to work with the ICMP only. So ICMP and IGMP, first of all, are very different. There is no relation between ICMP and IGMP. IGMP is entirely different protocol. So anyway, these are going to get encapsulated in IP only. So that's why generally the diagram is like this, that these packets are going to get encapsulated in IP only. And then at the network layer, since it is network layer only, if I talk about network layer protocols, then I do also have a protocol which is ARP, which is also a network layer protocol. Okay, this is also called network layer protocol, which is directly going to get encapsulated in Ethernet. So basically, this is going to get the support from IP, but this ARP is do not need any support from IP. So that's why the diagram is like this: ICMP on the top, IP, and then ARP. Why ICMP on the top? Because it needs the support from IP, but this IP, obviously, IP IP do not need any support. I mean, IP can directly get encapsulated in Ethernet, and ARP also directly get encapsulated in Ethernet. Okay. So these are the network layer protocols that we have. So I hope that is clear to everyone, that this is the ICMP packet that we just formed, and then this ICMP packet we are again going to put in the IP header. Okay. Now there are few points that we need to know about this ICMP error messages. First point is that there is no ICMP error message will be generated in response to the datagram carrying an ICMP error message, which means suppose you are sending some packet, and let's suppose this packet get dropped and this is sending ICMP message. But suppose for some reason this ICMP message also, okay, it reaches here, but this router is discarding the ICMP message. Router need to drop ICMP message. Suppose in this case, what will happen? If this router need to drop the ICMP message, then will there be another ICMP message that we are going to send to this? The answer is no. If the ICMP message is getting lost, then in that case, we are not going to send another ICMP message. That's what this point is saying. No ICMP error message will be generated in response to the datagram carrying just an ICMP error message. Okay. No ICMP error message will be generated for the fragmented datagram that is not the first fragment. So suppose you are sending some data, and okay, suppose you're sending some data, and then this has to get fragment into small fragments. It has to, let's suppose, get divided into small fragments. Then suppose this is the first fragment, this is the second one, third one, fourth one. Now suppose that one of the fragment get lost, maybe the second these reaches to the router, and the router have to discard, let's suppose, second. Then will it send the ICMP message? Answer is no. Okay, it will send ICMP message whenever it is discarding, if it has to discard the first fragment only. If it is not discarding the first fragment, then it will not send the ICMP message. Okay, so basically no ICMP error message will be generated datagram having datagram that is not the first fragment. If this is not the first fragment, I will not send the ICMP message. So if first have to discard, then we will send the ICMP message. If we have to discard second one, do we send the ICMP message? Answer is no. If we have to discard the third one, do we send the ICMP message? Answer is no. If we have to discard the fourth one, do we send the ICMP message? Answer is no. Okay. Why that is the case? Because I do not want to overburden it. Let's suppose if I have to discard all of them, then there is no point in sending ICMP message again and again. It will be very much overburden, right? And at the end, if let's suppose if you are not sending the ICMP message for 3, okay, and at the destination, if you are just getting 1, 2, and 4, then there will be obviously the timeout will get expire, right? So basically there is a reassembly timer. At that time, you are going to send the ICMP message, okay, because you will say that one of the fragment get expired. So this ICMP just not 100% providing you the error correcting or error detecting schemes. It is just helping you. Okay, somehow it is helping you. If fails to help, which means if ICMP error message itself get dropped, then there is no hope. I mean, that host may just have to wait and may be just retransmitting after the timeout and all, right? Okay, no ICMP message for the file of ICMP. Then what is the use of it? No, there is a use, right? I mean, this is just to help us in many scenarios. If there is a ICMP drop, if you are going to drop this ICMP message, then if you are again going to send the ICMP message to this router, that you are going to say that, okay, I'm going to, like, I have to drop your ICMP message, and then again if you are going to send this to this router, let's suppose this router also has to drop this packet, then this will send again ICMP message that, okay, I just have to drop your ICMP packet. Then let's suppose this router also has to drop your ICMP packet. Then because these routers are full, okay, they cannot accommodate any other packet, then they will keep on sending to each other. That's not the point, right? No, if it is dropping the ICMP message of this router, this is R1 and R2. If R1 is dropping the ICMP message of this R2, then if I at all have to generate the ICMP message, then this will send to R2 only, right? This will not send to destination. If it can send to destination, then why it is not even sending the packet coming from R2 itself, right? Why it will drop that packet and why it is sending by himself? So basically, like, I mean, these are just a design choice. Like the designers have made in this way that they said, like, there is no point in sending the ICMP message for the messages which are ICMP itself, because it will be a lot of traffic in the network if we do this. So ICMP is just a small help. It is not the 100% help that we are doing to the IP. Okay. If it is getting success in transmission, then it is okay. Otherwise, that's not a problem, because IP is anyway unreliable protocol. Okay. So if the datagram is having a multicast address, then also there is no ICMP message we will be generating. And similarly, if datagram is having some special addresses, maybe this or this, these are some special addresses. 000 means that I do not know my IP. Okay. And 127, this is we keep for the testing purpose. This is also some special address. So if there is some special IP address as a source address, then also we are not going to send any ICMP message, because obviously we cannot even send the ICMP message in these cases. Okay. So now let's just maybe try doing this question. What this question is saying: a program on a machine X attempts to open UDP connection to the port this one on a machine Y. Okay, so there is a machine X, there is a machine Y. Zero 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 is not any address. It is just saying that it is just helping us to match the entry. Okay, 0000 is just helping us to match the entry, because whatever the subnet mask you have, I mean the subnet mask is, let's suppose this is the, okay, the routing table. In the routing table we used to have some network ID, right? And then subnet mask. If subnet mask is, let's suppose, /24, then I'm going to say, okay, initial 24 bits are fixed, and then later bit you can make it to 0. Suppose the subnet mask itself is 0, and then this is 000, then it will match with any of the IP address that you have. Why? If I take any IP address, then if I'm going to say that, okay, none of the bits are fixed, you can change all of them to 0, then this 0 and this 0 are going to match. So basically it is just to help us to match one of the, at least one of the entry, which is the last entry. Okay, it's not any address in particular that form. It is just helping us to match one of the entry in the routing table. Okay, so this is not a default router address, it is just helping us. And then there will be a third entry that will tell you that where to forward, right? I mean, if you remember, there is a third entry which tells the interface number, or sometimes instead of just interface number, we also call interface IP. Okay, so basically I will tell you in today's lecture only what does this interface IP mean. So either we say, okay, just send it to interface 1, something like this, right? Or we also say that, okay, send it to this IP. So basically the 0.000 is not any IP or something. It is just helping us to match one of the entry, which is generally the last entry. And then the third entry will be the interface ID. It will send that, okay, send to Ethernet to this interface, something like this. Okay. So what this question is saying, okay, generally if we are putting the 000 in the IP packet in the source address, then we put 000 only when we do not know that field, right? If we do not know checksum, let's suppose, then we calculate the checksum using 000. If we do not know, let's suppose in case of RARP or something, DSCP, if we do not know the IP address, then we put 000, right? In case of IP address, because we know the MAC address, we do not know the IP address. So basically, if we do not know my IP address, then we will give this 000. Otherwise, we will not keep the 00. 000, if I'm putting in the source IP, then it means that I do not know the IP address, right? That's the only reason I will be putting the 00. Otherwise, why I will be putting the 00, right? Okay. So there is a machine X, there is a machine Y. Now, yeah, I will come to this 127 in one of the lecture. Okay. So now let's see what is happening here. A program on machine X attempt to open UDP connection to port 5376 on a machine Y. So here the port 5376 is this any program here wants to connect to this Y on this port, and a TCP connection to the port. Okay, so there are two connections that it wants to establish. There are two, okay, to JAD, a TCP connection to JAD on port 8632. However, there are no applications listening at the corresponding port on BY and JAD. So, okay, so BY and JAD server on this port, there is like this is not open. Okay, these ports are not open, these are closed. But still X wants to send some data. Then what will happen? The destination host will be unreachable. I mean, you are going to send the error message saying that destination host is unreachable because the port is unreachable. So ICMP port unreachable error will be generated by which one will generate? What do you think? What is the answer? Let me know quickly. No, you do not need to worry about whether TCP is reliable or not. Okay, so just think in terms of ICMP. It is at the level of IP layer only. I mean network layer only. So if the destination host is unreachable, you do not care whether it is TCP or UDP. You are going to send those 8 bytes. Those 8 bytes could be of TCP or UDP, right? These 8 bytes could be of TCP or UDP. The TCP or UDP are these will handle their error control at their level. I will tell you in today's lecture only that what do I mean by their level. I mean, each layer is having, if it is having the error control, flow control, then it's their own. I mean, it's on their own level, like, right? I mean, it does not need to do anything with the ICMP. So whenever you are sending some packet, if that is not reachable to buy and that is not reachable to, let's suppose, Z, then buy and Z both are going to send the ICMP error message. ICMP error. This is also going to send ICMP error. If these ports are closed, basically these, I mean, this server may be open, but the port is closed. No one is listening on these ports. So I think both will send, right? Yes, both will send. An ICMP packet port unreachable error will be generated by the both host. Okay. So I hope that is fine to everyone. Now, let's see another type of ICMP messages, which are ICMP query messages. So this is just ICMP error messages, but there are something called as ICMP query messages. Let me know if there is any doubt in ICMP error reporting messages. It is very easy. Like if something is you are not able to deliver, you are just going to send the ICMP error message. And you are not going to send the ICMP error message in these following situations. Okay. In these following situations, you are not going to send ICMP error message. Okay. Now let's see ICMP query messages. Sorry. So let me just put this also as a heading. Okay. Oh no. So let me just write it. So interestingly, query messages in ICMP can be used independently without a relation to IP datagram, which means discard any packet or something. Okay. So this is just a query message. You do not need to discard any packet for the query or some, I mean, you do not need to discard any packet to send a query message. If you're discarding a packet, then you are sending error message, not the query message. Okay. So it is independent in relation to the IP datagram, which means you do not need to discard the IP datagram to send this query message. Of course, a query message needs to be encapsulated in a datagram as a carrier. So obviously, like you will be sending the query message just like the just like you have sent this ICMP error message. Okay, in the similar way you are going to send the query message, but the mechanism that you are going to send only when you are going to discard, this is not correct. So basically, in the query message there will be no like these kind of things will not be there because you are not discarding anything. Okay, this is just for the error message. Contents of the data for the error message only. Okay, for the query message only this thing will be true, something like this, which means there will be ICMP header, but yeah, that will be carried in the IP header only. Okay, something like this. The query messages are used to probe or the test the liveness of the host or the router in the internet, which means, as I said, that in the query message what you are going to do, you are going to maybe check that, okay, are you alive, are you alive? That's what we are going to check. Maybe this is one of the application, and then this destination or maybe in between some router will say either if it is alive, then it will say yes I am, right? If it is not alive, it will not reply yes I am. So it can be used to check the liveliness. This is just one of the example. Okay, another example is that maybe you need to find the round trip time. Okay, one way time or the round trip time for the IP datagram between two devices, or even find out the whether the clock in the two devices synchronized or something like this, right? So naturally the query message comes in the pair request and reply. So what's going to happen? You are going to send some ICMP request query message, request message. Maybe the request could be anything. Maybe you are going to say that, are you alive? Something like this. It will reply, yes, I am. Maybe your request could be that my clock is this. Okay. I mean, maybe you just want to synchronize the clock that my clock time is this. And round trip time, you will also say that, okay, round trip time is generally this. Then are you in the sync with my clock? Something like this. Okay. You may also send some clock synchronization message. or maybe you just want to find out the round trip time. So how you are going to find out the round trip time? You are just going to send a packet, ICMP query packet with time as data. Okay, in that packet you will be just writing the time of sending. Okay, at what time you are sending this packet. Now the moment you receive the ICMP reply, then what you will do, you will immediately say that, okay, this is the data that I have sent. In that data you are going to have the time of sending, right? Time of sending. And then this ICMP reply will come at certain time. So what you will do, you will find the difference between the time at which this data has been just arrived, or this reply has been just arrived, from the time that you have just sent, right? In this that time you will be finding the data itself. Okay, and this way you can find out the round trip time, something like this, right? So you can also find the round trip time or the one-way time using the ICMP request and reply. ICMP request and reply are of type 8 and type 0, although the types are not important, are used by the host or the router to test the liveliness, as like these are the same, right? So maybe the liveliness or maybe the round trip time, these kind of things you can do using the ICMP request and reply. There are two popular applications for this. One is called ping, another one is called traceroute. Let's just quickly see those two popular applications. Okay. So I hope you understood that where I am, right? So what we are discussing is that we are discussing currently ICMP query messages, right? These are we are just sending without dropping any packet or something. Okay, we are just sending it to maybe know the liveliness, maybe to calculate the round trip time and all. So now let's just see two applications where we actually use this ICMP query message in practice. That is called ping and traceroute. Okay, so let's just see this ping and traceroute application. So ping is just one of the application where we are going to use the ICMP request and reply messages or the query message. We can use the ping program to find if the host is alive and responding. Okay, so it is just that, okay, I will say, are you alive? This is called ping. Are you alive? We use ping here to see how it uses ICMP packets. The source host sends the ICMP echo request message to the destination. If alive, it responds with the ICMP echo reply. That's all, right? The ping program sets the identifier field anyway, like this will just set the field and note that the ping can calculate the round trip time. It inserts the sending time in the data section, as I said, like, right? If you want to calculate the round trip time, what you will do, you will insert the sending time in the data section itself, in the data section of the message. When the packet arrives, it subtracts the arrival time from the departure time to get the round trip time. When you are going to get the packet, at that time you will say that, okay, at this time you receive the packet, and at what time you sent, you will get to know this from the data. Okay, at this time you have sent, so you can also calculate the round trip time using the ping. So this is just one practical uses where we are using ICMP echo message, echo request or reply message. So this is a command in Linux that is called ping. If you are going to do ping, then it does exactly same thing. Okay, so another is little interesting, which is traceroute. So this is very interesting. Traceroute, as the name suggests, it is tracing what? Route, right? I mean, name is also very clear, which is saying that you are actually going to trace the route. So what do I mean by tracing the route? Let me just show you. See. So let me just write it in this way so that it is clear in future also, that I don't know why I'm not able to copy today. Okay. So this is basically trace plus route, something like this. I mean, just to make it remember, this is trace and route. You are going to trace the route, which means you want to know that if you want to send from this host to this host, then what are the routers in between? Let's suppose you want to know what are the routers in between. Let's suppose you want to know, then what you will do, you will send one packet initially, and that packet will be having TTL as 1, right? Then yeah, that's very interesting. You are going to send TTL1 packet, and then like the moment it reaches here, the TTL will be 0. I mean, initially the TTL is 1, but when you are going to send it, at that time you will only decrement the TTL to 0, right? I mean, at the time of sending, you decrement the TTL to 0. The moment it receives this, if the TTL 0 has been received by the intermediate router, then what it will do? Do you remember? It will discard the packet saying that the TTL is 0. So it will send the ICMP. Okay, these are the ICMP error messages only. So this will send the ICMP error message. This is ICMP error message, which will say the time exceeded. The error message is of type time exceeded. Okay. And these are like from the sender, these are the ICMP echo messages basically. I mean, you are not going to send any data, you are just going to send some request, ICMP request with the TTL as 1. But the moment it reaches here, the TTL will be 0, and it is going to say that okay, TTL has been expired. So how what is the benefit of this? I will get to know that what is the IP address of the router that is just one hop away to me. Okay, this will just tell you what is the from at this point in time. I will get to know the IP address of the router that is just one hop away to me. Now next time I will set the TTL to be 2, and I will send the ICMP just hi. Echo means hi. Okay, hi message or hello message, and then this will say that okay, TTL has been 0. Now at this point in time I will get to know what is the IP address of the router which is 2 hop away to me. Similarly, I will get to know at this point in time what is the IP address of the router which is 3 hop away to me. Now, just tell me if I'm going TTL for 0, TTL 4 here. At this time, I'm going to get TTL 0, right? Now tell me, can I like will I be getting this error again if the TTL is 0 is the destination? If TTL is 0 is the destination, then do I get the error? No, right? So that's why like we need one hack here. I mean, I'm not going to get the error. So that's why what I will do, I will intentionally I will keep correct IP address. No, correct IP address so that I get to know where I'm going. Like I want to know between this and this only, right? Correct IP address. But can anyone fill this blank? But wrong port address. No, MAC it does not have to do anything with the MAC, right? MAC addresses will be at this point only. At this router has to deal with the MAC address of this particular host, right? Wrong port number. So basically, it will say destination unreachable. See this, it will say the destination is unreachable. So this is just one trick that we are going to play. Okay. And then finally, I will get to know that, okay, these are the hosts that are between. And then, I mean, in every packet, I will be putting the wrong port. Okay. In every packet, I do not know that TTL4 is designed for this, right? In every packet, I will put in the wrong packet. So this is just one of the application that is called traceroute. That is a mix of ICMP query message and ICMP error messages. What is the query here? These are the query messages, right? These are the query messages. What are the error? Error messages are coming from these routers, right? So these are the error messages. So this is just another application. So you can read this paragraph again, like the same thing that is written here. You can read this paragraph. Because these are not the error messages. I'm generating it without dropping any data, right? I'm generating it by myself. I'm not dropping any data. I'm not sending any ICMP error or something, right? So it is just some hello message that I'm sending with some TTL. Because this ICMP will at the end be encapsulated in the IP only. No, see, since these messages are not a result of any drop of the packet, so that's why these are not the error messages. These are just the query messages. You can send some of the data. So basically, in this ICMP packet here, sorry. So see here, in this ICMP packet itself, when you look at this header, so you can send some of the data. That's not the point. Okay, you can also send some of the data. Maybe in this data you can keep some of the things which is which is anything. Maybe you can keep sending time. Sending time you can keep. Okay. I mean, it depends on your application, what you want to do. You can do, you can keep some of the data. Okay. High ping indicates less network speed. High ping means, okay. So you can read this paragraph optionally if you want to. Now let's solve this question. This question has been asked in GATE 2005. What they are saying: trace route reports a possible route that is taken by the packet moving from some host A to a another host or some other host B. Okay, so you are going to trace the whole route. Which of the following options represent the technique used by the trace route to identify these hosts? So this question is particularly just for the trace route. Okay, so actually I did not know that this question is from the trace route. By some chance only I have just kept it just after the trace route. Okay, so anyway, so let's just read this. A progressively querying routers about the next router on the path to B using ICMP packet starting with the first router. Yes, you are going to querying routers about the next router on the path to B. Yes, I think this is true. Let's just see the B option also. By requiring each router to append the address to the ICMP packet as it forwards to the B. No, by requiring each router to append the address of the ICMP packet. No, it's not like that. You are not going to append any ICMP packet or something when you are going to forward to the B. No, it is basically, it's not in just one way. You are going to do multiple times. It is just saying you just do it in one way by appending something or something like that, right? So this B is wrong. C is saying by ensuring that ICMP reply packet is returned to A by the each router en route to B. So they are saying in between whatever routers you have, you make sure that you are going to get the ICMP packet, right? Is this correct? If this is A, this is B. From these routers, you are going to get ICMP reply packet. In ascending order of their hop distance from A. There is some problem in this option C. Can anyone tell me what is that problem? Are you going to get ICMP reply message or you are going to get ICMP error message or request reply message? So that's why this option is wrong. They are saying ICMP reply packet you are going to get. No, ICMP error packet you get, right? So that's why this C option is wrong. By locally computing the shortest path, okay, you cannot compute locally. So I think A is correct. So C, A is the correct answer. Actually, there was some debate in this question that why this C is not correct. Okay, and I mean at my time in 2016, I think, or maybe 6 years back. So at my time, like people were having some debate that why C option is not correct. So this is one of my comment that I put, that because their C option is saying ICMP reply packet is returned to A, which is wrong. TTL exceeded is not ICMP reply packet, it is ICMP error message. So that's why it makes this option wrong. That's why the C option is wrong, right? Otherwise, it is very confusing. Like, I mean, if you do not put the attention to this reply and error, you will think that C is correct, but C option is actually wrong. Okay, have you understood this? Let me know if there is any problem. Okay, so do you need some break before we start the next topic? Okay, so let's keep a break for 5 minutes and let's meet at I think 5:55. Sorry, 4:55. Okay, we will meet at 4:55. Thank you. Okay. So let's start a new topic, which is network address translation. And what do I mean by this? Let's just see. Okay. So suppose that you have, let's suppose many computers in your home. Okay. So let's suppose, for example, you have 1,000 computers. Like at your home, or maybe in some organization. Let's suppose at your home. Now, suppose that you do not have enough IPs. Okay. I mean, there are 1,000 computers that you have, but you do not have enough IPs. Let's suppose, for a hypothetical case, you just have one IP. Now, what you will do, if there are 1,000 computers, and if there is just one IP, then maybe if this wants to communicate to the internet, then you can assign that IP to this particular host, and then this can communicate. If this wants to communicate, then you can assign that IP to this particular host. That's what you can easily do, right? So this is just one of the scheme. But what we want, we basically want all of them to communicate to internet simultaneously. That's what we want. Okay. So our requirement is that, okay, I hope you're getting. So basically we can always assign one IP to one of the host, and we can always assign one IP to one of the host, and what we can do, and we can let this host connect to internet. I mean, that's what we can always do. But suppose we want all of the 1,000 hosts to connect to internet at the same time. Is this possible? Just tell me. If you just have one IP and you have 1,000 hosts, can those 1,000 hosts connect to the internet at the same time? Then the answer is yes. Is this possible? Then the answer is yes, using network address translation. Okay, NAT table. So what it does is basically, let's suppose you have any number of hosts here, maybe 1,000 hosts or anything, right? Let's suppose you have 1,000 hosts, and then there is a router which is a gateway to those 1,000 hosts. Now, what may so happen that you are sending the packet to just through the routers. I mean, all of these packets has to get sent to just through this router only. Okay, there is no other way, which means that this is the router that is standing on the gateway. Which means if the packet has to transmit to the outer internet, then it has to go through this router only. Let's suppose this is the gateway. Now, in this case, what you can do, if there are 1,000 hosts, you have just one IP. What you can do, you can say that, okay, if this host wants to send any packet, then you can assign the private IPs. Basically, this to those 1,000 hosts, you can assign some private IPs, which means like there are some reserved IP. Like I will tell you, okay, there are some reserved IP. You can assign those private IPs to those 1,000 hosts, private IP addresses, and then when this is sending something, then you will convert that private IP to your public IP, whatever the IP you have. Okay, you have. So for example, suppose that let's take this example. Let's suppose that there are many hosts that want to connect to the outer internet. Okay, let's suppose these are the many hosts, and there are few IP addresses which are called private IP addresses. You have given the private IP addresses to those hosts. These are the private IP addresses. Now, whenever you are sending, okay, this is the source IP. Obviously, these are the source IP. Whenever you are sending some packet, then the source IP address will be this much, right? I mean, when this router is receiving the packet, then you will see the source IP here will be this one only, which is 192 dot something, right? Will be this one. Destination IP will be decided by the host that it is sending to. Maybe if it let's suppose wants to connect to some server which is starting from 172.3.5, anything, right? Destination IP, it depends that to whom I want to connect. Now, what I will do, I will do one thing. I will take this packet where I have the source IP, destination IP, okay, which is coming like this. I will take this packet, and instead of sending that packet as it is, let's suppose there is one IP address that I only have one IP address, right? So instead of the source IP, I will just, obviously I cannot modify the destination IP. I will be modifying the source IP. Let's suppose the source IP, there is only one IP address that is available to me. Okay, just a second. Okay, let's suppose this is the only one IP address that is available to me. Then what can I do? Instead of the source IP, since these are the private IPs which are not allowed in the public domain, I mean, you cannot you cannot route through these IPs. So basically, internet doesn't know these IPs basically, right? Any router does not have any routing table that has these source IPs, because there are some special IPs that are just reserved for the private IP, which means any routing table cannot have routing for these entries. So basically, you are going to convert this IP to just one public IP that you have, which means in case of source IP, you are just going to write that much, okay, this IP address, and then you are going to send it, right? Then you are going to send the packet. So basically, whenever the packet is coming like this, you are just going to replace the source IP to the since these are the private IP, you are just going to replace the source IP to your public IP that you have, which is known to everyone. I mean, this is the IP that is known to internet. Okay. Now, if you do this, then what will happen? If this is sending packet, then also you are going to replace this with the source IP, right? This IP. If this is sending packet, then also you are going to replace with the only one source IP, because you just have only one source IP. What you can do, right? Let's suppose if you have three source IP, then yes, you can replace this with by some fixed IP1. You can replace this with IP2. You can replace this with IP3, right? If you have three IPs, then this private IP and public IP will be having some one-to-one mapping. But then there is no need to even map. If there is a one-to-one mapping, then why you are even converting, right? I mean, we can directly use the public IP at this place. Like, why we be needing the private IP at the first place, right? So basically, let's assume that you do not have enough public IPs. You just have only one public IP. Now, in this case, what's going to happen? All of these packets are going to have the same IP, right? The destination IP could be different, but all of these packets are going to have the same. All of these packets are going to have same IP, right? Whenever they are going out. Now, what will happen? Whenever packet is coming back to this router, at that time, since this IP address is of this router IP address, then at that time that is okay. I mean, if the packet is coming back, then it can come back to the router itself using this source IP, which is 213.18.123.100. Let's suppose using this IP that return at the return time, it can come back to this router. But now this router will get confused that it should forward to this one, or this one. You're getting my point? See what is happening here. This is, let's suppose, some IP. Okay. These are the three IPs. Maybe let me call it some anything. Okay. Maybe 192.168.1, something like this. Okay. This is 192.168.2.0 or any IP. Okay. This is just some IPs that I have. Now .0.0, let's suppose some IPs that we have. Now all of them, if all of them are going to get the same public IP, then will there be a problem in forwarding? Tell me. If all of them are going to get same public IP, which is this, then I think the forwarding problem will not be there. At least you can reach to the destination using this public IP, and that's okay. I mean, there will not be any problem in this direction. Is this okay to everyone? if all of them are going to finally get this IP, if you are going to replace these IPs with this IP, then this direction is fine, because this direction just need your destination host, destination port, and all of this we are not modifying, obviously, right? Destination thing we are not modifying, only the source IP we are modifying, which is this. Destination I will not modify, definitely. Why will I modify the destination, right? Is this okay to everyone? So this direction is very smooth. But whenever the packet is coming back, okay, whenever the packet is coming back, or the reply is coming, at that time this router will get confused, right? Suppose now you are getting the packet where the packet will be having this as a destination IP, right? I mean, earlier it was a source IP, now it will be a destination IP. Anyway, now this router will get confused that this packet is meant for this one, or this one, because you do not I mean, how can you even remember that? Okay, you are because you are mapping this to also this to also this to also this. Then whenever a packet is coming, then in this direction there will be a problem. How can it distribute to one of them? Have you understood the problem here? Let me know if things are clear to everyone, that what I'm trying to convey. Okay, Sumant, is this okay to you? So basically, we are sending some packet, and if all of them are sending a packet, if I'm mapping to the same IP, at least you can go from this direction. That's not a problem. But the packet, whenever the reply is coming back, at that time this router will get confused to whom I should be mapping, because you should be just, this packet must be designed for only one of the network, right? Okay. See, whenever the reply is coming, the reply will be having this as a destination IP. Now you need to distribute this reply to only one of them, because this must be a reply to just one of them. Now, to whom you should be giving this reply? You will get confused. I mean, if there are, let's suppose, 3 IPs that I'm maintaining, for each I'm maintaining just one IP. Okay, let's take very simple case, 1-to-1 case. Okay, let's take very simple case where the mapping is 1-to-1. Which means that if, let's suppose, if this is the IP, maybe just a second. So suppose if this is the IP, then I will map to some other IP. If this is the IP, then I will be mapping probably to some other IP. Let's suppose if that's the case. Okay, if this is the IP, then I will be mapping to some other IP. Maybe I'm mapping, let's suppose, 200 or something here 300 or some, sorry, 300 could not be there, but yeah, maybe 180 or something here. Let's suppose it is something 170 or something like, for every IP I'm having a different IP. Now whenever a packet is coming to you, okay, at the reply time, it will be having, since it was the IP, or maybe it was the IP, maybe it was the IP, it will be having one of the IP. Maybe let's suppose it is having 170 or something. Then you get to know, okay, this 170 means this IP. Internally it means that this IP. Then you can easily distinguish that this 170 packet is made for whom, right? If there is a 1-to-1 mapping, one mapping, then in this case there is no problem of distinguishing. Like at the incoming time, you can easily distinguish that this packet is meant for whom. This packet is meant for this one, or this one. Because if 170 is there, then you will get to know, okay, it is for first one. If 180 is there, then you will get to know, okay, it is for second one. If 200 is there, then you will get to know, okay, it is for third one. But suppose all of them are just mapping to the same one. Now at this, like in this forward direction, there will not be any problem, because that is dependent on the destination IP and all. So at the forward direction, there will not be a problem. But whenever you are getting a reply, at that time you do not know that you have mapped that, I mean, which reply it is. It is this one, first one, second one, third one. While send router won't change the sender IP. So it is changing the sender IP. That's the thing, right? I mean, it is changing this private IP to some public IP. That's what I'm saying. This IP in this packet, there will be a source IP. Okay. Earlier the source IP is this, but now after this router, the source IP will be this. See here, that's what I have written. The source IP is 192, but after this router, the source IP is 213. Okay. That is true for everyone. Okay. For every packet, I'm replacing the source IP. Destination things I will never ever touch. Only the source IP I'm touching. Why I'm doing so? Because these IPs are private IP. These are not known for the for any router or anything. But yeah, this is some public IP which is known to everyone. Okay, using this IP, like I can do some routing and all. So at that time, if I'm receiving this IP, then maybe I will be able to reach to this router, but this router will not be able to distinguish that to whom I should be mapping, right? Let me know if that is okay to everyone. It's very easy. Like I don't know where is the confusion. It is very straightforward. Like if you are mapping something to this, if there is a many to one mapping, then given this, you do not know whether it is this or this, right? Now, now suppose that some packet is coming, then I will get confused. Then obviously this strategy will not work. I mean, if there are multiple IPs getting mapped to the same IP, then this kind of strategy seem not to be work, right? So should there be one-to-one mapping always? If there is a one-to-one mapping, then why I even need this? I mean, if I need exactly same number of the private IP as the public IP, or the exactly same number of public IP as the private IP, then there is no benefit of having this translation and all, right? I want to have just one IP here and any number of IPs here. That's what I want. But it seems like if I do so, then this naive strategy is not working. I need to do some modification to this strategy. Can anyone suggest me any modification so that at the return time I can be 100% clear that okay, this packet is designed for, okay, even though the IP is the same, this packet I can be clear that this is for this. Any idea? So here I will be taking a help of port number. Okay, let's just see that how the port number is helping here. Taking help of port number port translation. Let's just see that how port number is helping us. Suppose, okay, so only see again, I'm only talking about the source. Okay, destination port, destination IP, these have nothing to do with NAT. Okay, so port number or any IP or anything, this is just for the source. Destination thing I cannot change. This is for the source only. Okay, so suppose that this is one host which is running on port number, let's suppose 22378, some port number. Then what will I do? Interestingly, what will I do? I will make a table. Okay, in that table, so basically I mean there must be some port number along with the IP addresses, so let's just write those port number also. And then now it is actually very easy. Now let me tell you how. See what I will do. I will make a table. Okay, or maybe like table, I will come to this table in a little while. So what will I do? Can anyone suggest me? Yes, it will save the entry. Yes, obviously it will save the entry that what mapping it has done. So what will I do? Let's suppose these are the different ports 3573. Let's suppose 4930. Okay, these are the three ports. What will I do? Whenever a packet is coming, okay, so it must be having the source destination IP, I mean in the packet at the sending time. Let me tell you that what is happening step by step. See, this is at the sending time. Okay, before the router, after the router, this is the sending time. This is at the receiving time. Okay, I will make the receiving time just in a minute. So basically before before the router, I just have this. Okay, before the router. After the router, what do I have? After the router, I do have this. Okay, so after the router, I do have this, which is this is true for every packet, which means for another packets also. Okay, just a second. So for every packet, this is true, that before the router and after the router, this is the story. So now let's suppose this IP address is to, okay, this could be anything. I'm just writing some random IP addresses and random port numbers. So suppose this IP address is some 2, 3, this port number is 3573, this is 4930. Okay. And after the router, the IP addresses are same, but the port numbers will be different. I mean, I am not changing the port number here. Okay. I'm only changing the IP address, which is 3573 4930. Is this okay to everyone? That I'm just changing the IP address here. Let me know. So these are some empirical port numbers, which at the client side, you can have any random port number. But at the server side, there's a fixed port number, which means for HTTP, destination port numbers are very much fixed. For HTTP, I think we use the port number 80 or something. At the server side, the port number is very much fixed. But at the client side, this is just any port that can work with you. Okay. So let me know if this mapping is clear to everyone. I'm sending some IP addresses. So IP address I will change. I will not change the port number. Now, earlier, what was the problem that was with me? If some packet is coming, I was confused that which one to map. Now, what will I do? If some packet is coming, then I will check what are the IP and the port. If the IP and port is this, then I will get to know, oh, it means that now I got the one-to-one mapping, right? I mean, just using a port number. It means that since this is the port, using the port, basically I'm doing the mapping. So I will get to know, oh, if this is the port, it means that this is the first one, right? If this is the port, it means the first one. If this is the port, right? If this is the port, using the port, I can distinguish basically. Earlier I was not able to distinguish, but now I can easily distinguish using the port. I can say that, oh, if this port, it means it is the second one. If this port, then it means it is the third one. Let me know if that is fine to everyone. So using the port, now I'm able to distinguish. Yes, but there is a small problem in this also. Suppose two routers are having, oh sorry, two hosts are having the same port. Then what will I do? If some packet is coming, then it will be having this, and I will be confused whether this means this one or this one, right? The third possibility is eliminated. I completely agree, but there are two possibilities. Still, there are two possibilities. That is why what will I do? Instead of keeping these ports same, okay? So I will do one thing, which is the final modification that we are going to do. We are going to say that let me just for the this for the forwarding packet, okay, for the packet that I'm forwarding to the internet, let's just map this port also, which means let's suppose port number 1, port number 2, something like this. Okay, this is the port number 3. Okay, which means if some packet is coming with the port number 1, I'm 100% sure it is the first one. If it is port number 2, I'm 100% sure it is the second one. And what is the real port? I mean, like whenever it is coming, then at this time also it will come from here, right? I mean, it will pass through the router. So at this router should map these things again back to the original thing. Then I will be maintaining a table. Okay, see here, see this, what is happening here. Here in this A, so suppose you are sending some packet from this is the first one, right? So you are sending some packet from this to this. Now just look at the source. Okay, don't look at the destination, because destination I'm never ever going to touch anyway. NAT, this is the NAT table, this is the NAT router, and this router never going to touch the destination. Destination, source, port, everything is first in the destination. Destination I cannot even touch. From the source perspective, what will I do? It is having a mapping, something like this. It will say that, okay, this is the source. Okay, inside this is the inside, and this is the WAN, means wide area network, that we might talk about. So basically you can just think like this. This is a public IP. Okay, public address. This is the private address. LAN means local. Okay, locally you are using this, but publicly public, and this is private. So private or the locally you are using this, but publicly you are going to say that this is the IP and this is the port. Okay, suppose this is the mapping that you are doing. Now, whenever you are going to receive something with this IP and this port, which is unique, right? I mean, since IP, let's suppose I just have one IP, okay, which means that my table will look like this. See, my table will look something like this. Okay, so let me probably remove most of the things just for the sake of understanding. Okay, let's suppose I do not need this for now. Okay, so my table will say that I do have an entry which is mapping from private private IP, whatever IP I have as a private, and the real port number. This is the real port number that I have, right? I mean, on this port, the host is listening. This is real port number. I will use the public IP and some fake port number. Okay, this is some fake port number. I mean, I can use at the client side, I can use any port number, doesn't matter, right? I will be using some fake port number. So my translation table will look like this. See, it will be basically having, let's suppose I do have only one IP, it will be having only one IP only, right? Only one IP and different port numbers. Okay, different numbers, some fake port number, like doesn't matter, right? I can give any port number. So some fake port number, let me give, maybe let me say it is probably 2, it is 3, it is 4. And then the private IP and the port number could be anything. Okay, the private IP and for the port number could be 10.0.0 maybe .2, and the port number could be anything 3973, whatever, right? So whenever you are receiving this, you know that okay, this is exactly mapping to this, not to anything else. So whenever at the incoming time, you are 100% sure that this entry, you will convert that whenever you are sending from this, you will convert this entry, which is 138.76.29.7 comma 5002, you will convert this to 10.0.0.223973, right? I mean, at incoming time, you are 100% sure that how to convert. Okay, I don't know like if the directions are clear, because see here they are using this direction for the incoming outgoing, but yeah, this is at the incoming time. Okay, this is your private network. Let me know if that is clear. See, whatever IP you have, whatever the port number you have, you must be having some private IP, you must be having some port number. I will convert this private IP to public IP, and then I can keep this port as it is. See, I try to keep this port as it is. If you remember, see here, we try to keep this port as it is, right? This, but there was a problem in this scheme. What was the problem? Can anyone recall me the problem? Problem is that if two ports are same here, then there will be a problem, right? Then if I keep them as it is, then there will be a problem. So that's why I said, okay, let me just put some fake port number. Okay, let me not keep them as it is. So if I do so, so basically there will be some any private IP here I will be having, and then any real port number. Okay, this is the real port number on which it is actually listening. So I will convert this IP to my public IP, and then some dummy, okay, some dummy port number I will give, which will be able to discriminate. So whenever I'm getting a packet with this, I will get to know, okay, this means there will be one-to-one mapping now. This means this one only. Actually, this means this one only. Like that, I can distinguish. Let me know if that is fine to everyone. Should we do some question maybe? After that, it will be more clear, right? So let's see this diagram. See, in this diagram, I do have these packets, and then if I'm sending these packets through this NAT router, this router will be having some NAT table, and then this will be converting the this IP to this, and then whatever the port number, let's not worry about the port number. I mean, I have not written it here, maybe 3579, something like this. I will put some dummy port number here, so that whenever I receive this, then I will be having something like this. Then I will get to know, okay, this dummy port basically means that this particularly means this. So I do have the one-to-one mapping always. Okay, even though there is just one public IP, still I'm having the one-to-one mapping. Okay, so I mean, there will be some private address, there will be some real port, you can say some I mean, just to have this, you can say just actually it is listening on this port. Okay, and then there will be some public address, and then I can have, just to send this out, I can have some dummy port. Okay, some dummy port. I can say that okay, it is maybe 101, 102, something like this, right? So whenever a packet, whenever I'm sending a packet with this configuration, it is actually get sent using this configuration. I'm replacing the IP, and I'm replacing the port also. Okay, whenever I want to send a packet with this configuration, I will actually send a packet with this configuration, right? Now this is for the sending. Whenever I'm receiving, if I'm receiving with this configuration, it means that actually it is this configuration. It is very nice, right? It is one-to-one mapping. Now I'm replacing the IPs. Everything I'm replacing with just one IP. If I just have one IP, and then I'm giving a dummy port. Very nice idea, very elegant idea, using which I am able to solve my translation problem. Let me know if there is any problem in this. Okay. So see, that's what it is happening. That this is the first step. There's a source, and there's some real port that you have. You will replace this with IP. There's just some dummy port, right? This is some dummy port. And then whenever you're receiving, then this thing will be actually destination. Then you will get to know, oh, this combination means this one only. Then this will actually convert to this one only. See here, this thing get converted to this thing only. So now this becomes destination, but yeah, that is okay. Is this fine? So basically there are some reserved addresses, right? So these addresses you can use as a private IP. Maybe you can use these addresses. Maybe you can use these addresses. Maybe you can use these addresses. So these addresses are never used for the routing purpose. These addresses you can use as a private addresses only. Okay. So what it is helping me? How NAT is helping me in solving which kind of problem? If you are having many hosts and you are having lesser IPs, then you can do this using the NAT, right? I mean, you can still connect all the hosts to the internet using the NAT. So there are many IPs and many hosts, right? If we have many hosts and very few or even just one IP, then we can use NAT. Oh, okay. Or in that case, NAT help us to communicate to internet. In that case, right? I hope that's fine to everyone. So basically, if you are having lesser IPs, but this is not a long-term solution. Let's just see a long-term and a short-term solution. This is just a short-term solution. Internet will eventually run out of the IPv4 addresses in just few years, because there are many devices that are coming every day, right? In every house, we are going to have many devices, and the IP addresses are not that much enough. See, I don't know the exact number, but I think the internet is not accessible to more than 10% of the whole population in this world. But as we advance the technology, then this internet is going to spread to the more people, right? If it is 10% today, then maybe in just 10 years it will be, maybe, I don't know, maybe the 30 to 40% like that, right? So maybe in just few years, maybe after 50 years, that IPv4 addresses will get eventually run out. So in that case, I can use NAT, but it's just a short-term solution. But the long-term solution is IPv6. That is having, there is IPv4 was having 32-bit address. It is having 128-bit of addresses. I think it will take even 1,000 or maybe 50,000 years to consume all of these IPv6 addresses. So the permanent solution is that we should be going for the IPv6. Okay, if we are running short of IP addresses, then the fixed permanent solution is that we should be going for the IPv6. Okay, so let's do some questions. So this figure at the right shows two residential networks with the routers that implement NAT. Okay, so these are the two routers which are implementing network address translation. Suppose host A is connected to a web server at host E. Host A is connected to a web server. Okay, so A is connecting to this E. Suppose in the left hand NAT table, add the entries that would allow A to communicate with E. So they want to add some entries here, and you may choose any port numbers you like. So as a dummy port, you can choose anything. I think in the left and right, they might be asking for the both. Okay, so we need to add some NAT table here. So external port means, I think external port, I don't know what do they mean external port. I think this is just a dummy port here. So can you do this? So this is the internal port that we are using. So internal IP is this. Port could be anything, right? Let's suppose internal IP is this 10.1.1.1. Let's suppose port is something which is, I don't know, maybe this is the actual port 3.1. Okay, this is the actual port that we have. Now the external IP will be how much? 1.2.3.4, and the port you can choose any port, it is up to you, right? Yeah, 101 will also be fine. So you can map this combination to this combination. Similarly, you can map 10.1.1.2 comma, maybe it is 500 some other port, you can map this to 1.2.3.4 to 102, something like this, right? That's what you can do. Okay, the IP addresses are not written currently, but yeah, that is fine. So this is the internal one, comma 80. Okay, this is some server, D is also some server which is basically running on the port 80, and yeah, you are mapping that to port 80 only. So basically, if it is a server, then generally we do not change this port number. If this is a client, then we change the port number. We can have some dummy port number. If this is a server, then generally we do not change those port numbers. I mean, because on one generally, I mean, in this area there will be only just one server. I think that is the case, because they have not changed this 80. Maybe because this D is a server. Okay, so anyway, let's just go to the next question, what they're asking. Show the values of the addresses and the port fields in the diagram below for a typical packet sent by host A. Okay, so let me copy this diagram. Okay, what they're saying, that what are the source address, destination address, source ports and destination port for the typical packet sent by host A. Okay, whenever you're sending, what will the source address? Can anyone tell me? It will be 10.1.1.1, right? What will the destination address? Let's suppose it wants to connect to E, then destination address will be 4.3.2.1. Right, one second, let me just copy this so that I mean, there will be a separate page, blank page. Yeah, so let me just modify this now. So it is 10.1.1.1, it is 4.3.2.1. what is the source port here? Maybe anything, right? I think it is working on the port which is 7654. Let's suppose this is 7654. What is the destination port? It wants to connect. Okay, this again could be anything. Maybe I think this is 80 or something. Okay, let's suppose this is 80. Suppose this wants to connect to E and this is 80. Now they're saying that this is the packet that is sent by A. Now after this router, what will the packet? What will the source address? Source address will be 1.2.3.4. What will be the destination address? It will be same, right? You do not touch the destination thing. Destination port also will send. What will the source port? Maybe you will be having some dummy port. Okay, 6789. Let's suppose this is the 6789. This is some dummy port that you have. Is this okay to everyone? Okay, right. This is the answer. Now let's continue this question. What they are saying. Suppose, so maybe I can copy this diagram. Yeah. So they are saying, suppose the user in the right hand network wants to run a web server on host D. On the right hand network wants to run a web server on host D. So D is some web server. Add an entry to the right hand table that would allow the remote connection to the web server. Okay. So here, what should we be writing that will allow the remote connection to this web server? Assume host V connects to this web server D. Add an entry to the left hand NAT table for this connection. Okay. So suppose that this V wants to send some packet to this D. Then what are the ports that you will be having? Okay. So this is a routing table. I mean, this is a NAT table at this D end. So if D is sending some packet, then tell me if D is sending some packet with port number 80, right? Now at that time, will be having some dummy port number if D is a server? If D is a server, then these are the designated port. I mean, 80 is for HTTP or something, right? If D is sending some packet, then you cannot have some dummy port basically. If it is for client, it doesn't matter actually. But if it is a server, then this port will be as it is, right? So this, the external port or the public port, it cannot be a dummy port. It must be 80 only. Okay, if it is 80. Now what is the IP? Now IP is 10.1.1.4, 80. It should be mapping to 80. Now the IP address, the public IP address could be anything, but the port number you cannot change. Because whenever D is sending some data, then I should be knowing that, okay, this request has been fulfilled by the HTTP server, right? Not some random client or something like this. Have you understood? No, you may be having multiple servers. It's not like that. But generally, just a one server for that is a web server, just one server that is a FTP server, something like this. Because if the port numbers are same, then there will be problem. That's why we need to keep just one server of one type that is having just one port, which is 80, 81, something like this. Because if port numbers are same, then there might be some problem. If there are different IP, then I can have different servers also. See, if there is just one IP, then it is a problem. But if there are two IP or three IPs, then I can have multiple server of the same type also. Then I think I can map, right? It is just that I can map or not. So I hope that is clear. So this entry is fine to everyone. Now they are saying if B wants to send some packet, then what will the entry here? Okay, so maybe I will be having here entry 10.1.1.2, comma any random port. Okay, will get converted to any random port, right? I mean any dummy port. So let me see the answer actually. So yeah, this is the answer where I'm having this B IP address, and this is the actual port which I'm converting to some dummy port, right? This is some dummy port. Okay. Now let's see other questions. Now what they are saying: show the address and the port field to the typical packet leaving host B. Okay, suppose something is leaving B. So leaving B, this is the packet that is leaving B. The fields in the same packet as it passes through the public network. Okay, the same packet, same after passing NAT basically. Okay, this is the same packet, and then this is the same packet that is delivered to B. Okay, same packet reaches to D. So basically, these are the three fields that we need to fill. Let me just copy this. Based on this, we can fill the entries, right? Okay. Can you fill the entries now? So whenever you are whenever it is at B, then the source IP and the port number should be like this, I think, right? And destination IP and the port number should be of D. Destination IP is this, and the port number is 80, right? So I think you can fill out these entries. Do you want to do this as an homework? Because I have the answers on the next slide. Maybe you can just try it out, right? Just try it out as an homework. Answers are on the next slide. This is just an easy question. You can try it out. Based on this, you need to fill out all the entries. Okay. So now today I wanted to discuss one last topic, that how all the layers are working in unison, which means all together how it is happening. So let's suppose there are 3 networks, and these are networks are having some IP addresses and all, and how these, let's suppose there are there is some router that is connected to that is connecting these 2 networks and all, and there is some host and all. So how these are communicating, I wanted to talk about it, but I think the time is over. So we will be talking about this topic tomorrow. Okay. So how all the layers are working together. If there is a host here, and there is a host that wants to communicate to this host, and let's suppose there are a couple of routers, a couple of networks in between, then how this is communicating and how the all layers are working together. We will talk about this tomorrow. Okay. So yeah, thank you everyone. So let's meet tomorrow. Thank you.